Αγαπητοί συνάδελφοι, κυρίες και κύριοι, αγαπητή Ελένη, εκ μέρους του Προέδρου και του Διοικητικού Συμβουλίου του ΙΤΕ θα ήθελα να σας καλωσορίσω στην πέμπτη από τη σειρά των διαλέξεων που διοργανώνουμε για να τιμήσουμε το έργο και τη μνήμη του αλυσμόνητου Στέλιου Ορφανουδάκη. Ο σημερινός μας ομιλητής είναι ένας διακεκριμένος μαθηματικός, από παλιά φίλος και συνεργάτης του ΙΤΕ, ο καθηγητής του Πανεπιστημίου του Stanford, Γιώργος Παπανικολάου. Έχουν περάσει κιόλας 8 χρόνια από τότε που μας άφησε ο Στέλιος και τον θυμόμαστε βέβαια διαρκώς για το έργο του και το όραμά του και τη θερμή ανθρώπινη παρουσία του και βεβαίως για το κουράγιο και την αισιοδοξία του. Το θέμα της ομιλίας του κ. Παπανικολάου σήμερα είναι απεικονιστική σε σύνθετα μέσα, Imaging in Complex Media, και αυτό ήταν ένα από τα κύρια ενδιαφέροντα του Στέλιου Ορφανουδάκη, ιδίως βεβαίως στην περιοχή των ιατρικών απεικονίσεων. Να θυμηθούμε ότι ο Στέλιος ξεκίνησε την ακαδημαϊκή του σταδιοδρομία στο Πανεπιστήμιο Yale στην Αμερική, όπου εκτός από καθηγητής στην Επιστήμη των Υπολογιστών στο τμήμα ηλεκτρολόγων μηχανικών, ίδρυσε και διεύθυνε το τμήμα διαγνωστικής απεικόνησης της ιατρικής σχολής του Yale, μιας μεγάλης ιατρικής σχολής. Η έρευνά του κατά τη δεκαετία του 70 αφορούσε κυρίως υπολογιστική αξονική τομογραφία και οι συνεργασίες του στη σχολή του Yale με πρωτοπόρους επιστήμονες της εποχής, στην περιοχή της ιατρικής απεικονιστικής, δημιούργησαν ένα πραγματικά μοναδικό ερευνητικό περιβάλλον που συνέβαλε έτσι σημαντικά στην κλινική εφαρμογή νέων απεικονιστικών τεχνικών, που άλλαξαν πραγματικά το πρόσωπο της διαγνωστικής ιατρικής και το σχεδιασμό των θεραπείων. Ένα χαρακτηριστικό παράδειγμα της απήχησης της δουλειάς του Στέλιου, σύμφωνα με πληροφορίες που πήρα από τον κύριο Κώστα Μαριά και τον καθηγητή της ακτινολογίας, τον κύριο Καραντάνα, αφορά την εργασία του Στέλιου Bone Mineral Analysis Using Single Energy Computed Tomography του 1979, που άνοιξε καινούριους δρόμους στην κατανόηση και έγκαιρη διάγνωση της οστεοπόρωσης. Η μελέτη αυτή, που ήταν πρωτοπόρα με ποσοτική ανάλυση βασισμένη στην αξονική τομογραφία, ήταν η πρώτη μελέτη που έδινε πληροφορίες με απεικονιστικές τεχνικές για την ποσότητα των οστικών αλάτων στο σκελετό. Και αυτή η εργασία ακολουθήθηκε από πολλές μελέτες που βασίστηκαν στην τεχνική και ακόμα και σήμερα έχει εφαρμογές. Και βέβαια είναι γνωστό ότι μετά την επιστροφή του στην Κρήτη το 1985, ο Στέλιος ίδρυσε στο Ινστιτούτο Πληροφορικής του ΙΤΕ το Εργαστήριο Πληροφορικής, Ιατρικής Πληροφορικής και Τηλεματικών Εφαρμογών, του οποίου η μετεξέλιξη και βεβαίως και οι ερευνητικές ομάδες που προήλθαν από αυτό εξακολουθούν να υπάρχουν και να διακρίνονται. Θα έλεγα ότι ο Στέλιος συνέβαλε όσο κανείς άλλος για να τεθούν οι βάσεις γενικότερα της πληροφορικής στην υγεία στη χώρα μας. Ο σημερινός μας ομιλητής, ο Γιώργος Παπανικολάου, γεννήθηκε στην Αθήνα το 1943, σπούδασε στην Αμερική και πήρε το διδακτορικό του στα μαθηματικά το 1969 από το Courant Institute στο New York University, NYU. Για πολλά χρόνια ήταν καθηγητής στο NYU και από το 1993 διδάσκει στο Stanford. Έχει τιμηθεί με πολλές διακρίσεις και βραβεία, μεταξύ των άλλων με το βραβείο Von Neumann του Siam, το βραβείο William Benter Prize in Applied Mathematics. Υπήρξε προσκεκλημένος κεντρικός ομιλητής σε πολλά μεγάλα διεθνή συνέδρια μαθηματικών και φυσικής. Είναι μέλος της Αμερικάνικης National Academy of Science και επίτιμος διδάκτορας του Πανεπιστημίου Παρίσι 7 και του Πανεπιστημίου Αθηνών. Η δουλειά του Γιώργου Παπανικολάου έχει σημαδέψει κυριολεκτικά όλο το πεδίο των εφαρμοσμένων μαθηματικών, με πολύ σημαντικές συνεισφορές, παραδείγματος χάρη σε κυματικά προβλήματα, αλλά και σε προβλήματα παραβολικά, με διάχυση, σε μη ομογενή, σύνθετα ή τυχαία μέσα, στη μαθηματική ανάλυση των φαινομένων πολλαπλών κλιμάκων που εμφανίζονται σε αυτά τα προβλήματα, και οι εφαρμογές της δουλειάς του προέρχονται μεταξύ των άλλων από τη διάδοση ηλεκτρομαγνητικών κυμάτων, την υποβρύχια ακουστική, τη γεωφυσική και τη σεισμολογία, καθώς και τη διάχυση σε πορόδι μέσα. Έχει μελετήσει γραμμικά και μη γραμμικά προβλήματα, ευθέα και αντίστροφα προβλήματα, καθώς και στοχαστικές διαφορικές εξώσεις με εφαρμογές σε χρηματοοικονομικά μοντέλα. Η σημερινή του ομιλία αφορά τη δουλειά του πάνω στη μαθηματική πλευρά της απεικόνησης, απεικονιστικής, imaging στα ελληνικά, σε σύνθετα μέσα. Στο ΙΤΕ βέβαια πολλές ομάδες ερευνητικές ασχολούνται με imaging διαφόρων μορφών και πολλές εφαρμογές, και imaging σημαίνει για διαφορετικά group διαφορετικά πράγματα. Αλλά ας μου επιτρέπει να πω ότι αν θέλουμε να καταλάβουμε τα προβλήματα σε βάθος, θα χρειαστούμε αργά ή γρήγορα, δύσκολα και πολλά μαθηματικά, και βεβαίως θα χρειαστούμε να εκτελέσουμε πολλούς υπολογισμούς, πάρα πολλούς υπολογισμούς, και να διαχειριστούμε ένα μεγάλο όγκο δεδομένων. Και ο Γιώργος θα μας δώσει μια γεύση σήμερα της πολυπλοκότητας αυτών των προβλημάτων. Ladies and gentlemen, this is the fifth in a series of distinguished lectures that we organize in Fourth, the memory of Stelios Orphanoudakis, our late president of Fourth. And among other areas that Stelios studied was imaging, medical imaging. He was a professor of medical imaging and computer science at Yale before coming to Crete. And when he came to Crete, he was one of the foremost people here in Greece in medical imaging and in general the application of telematics and computer science in medicine. And it's very apt that our today's speaker is George Papanicolaou from Stanford, who is going to speak on imaging in complex media in this series of lectures.
Okay. Ευχαριστώ πολύ. Ευχαριστώ πάρα πολύ, Βασίλη, για την, πρώτα απ' όλα για την πρόσκληση. Ευχαριστώ το ΙΤΕ για την πρόσκληση. Ευχαριστώ επίσης για την τιμή να δώσω αυτή την ομιλία στη σειρά ομιλιών για τον Στέλιο Ορφανιουδάκη, τον οποίο δεν τον ήξερα προσωπικά, αλλά η εργασία του είναι πραγματικά πρωτοποριακή εργασία. I'm going to talk about imaging in complex media, but not of the medical type, medical imaging, focused towards medical applications. Although I could have done that, I decided to talk about applications that have their focus in geophysics, come from geophysics. Towards the end, after I describe this correlation-based imaging, noise-based imaging, I will also mention the medical applications that the subject has, which are developing very rapidly and could be the choice application of correlation-based imaging. So let me start by first mentioning, as Vasilis pointed out, imaging means many different things to different people, to different groups. And I'm going to talk about imaging with ambient noise, passive imaging, imaging that's passive, where the energy that illuminates the subject to be imaged, the object to be imaged, is noise, or appears to be noise, appears to be something random, incoherent, something that's out there that can be used opportunistically. Now, the key words in imaging that I want you to pay attention to are, first of all, that we're talking about passive imaging, passive sensors. The sensors are passive. There's no active illumination taking place. That's the first one. The second one is coherent imaging. Coherent imaging means that the signals that we receive are highly resolved. To give you an example, in the human auditory system, when we speak and listen to each other, the signals that are recorded and reach our brains are coherent signals. We know when the signal arrives, when a sound comes first, and then the following sounds come after that. But when the human visual system is an incoherent imaging system, we do not, when I see you, I perceive the different reflectivity that you have, but the information that is recorded in my retina is information about the intensity of the light that goes there. I do not have phase information. So here I'm going to talk about coherent imaging as opposed to incoherent imaging. Usually as the frequency of the signal that is being recorded increases, there comes a threshold depending on the technology of the current time where it begins to be incoherent. For example, in X-ray tomography, that's all incoherent imaging. Anything above the optical range tends to be incoherent at present. Noise source illumination, that's what I was just saying before. We're not pointing a light at you. The source is ambient noise. That will be a very important part of what I have to say later on. The role of the medium, deterministic of random. Are we talking about trying to detect something in a homogeneous medium or something in an inhomogeneous medium? And finally, the role of where are the auxiliary arrays? Where are the sensors placed? Where do we place the sensors? I mean, the physiology of sensor placement is different. I mean, our sensor system is dominated by our ears and our eyes. Other animals have other sensor systems, ultrasonic systems. The bats and the dolphins have very highly evolved ultrasound systems for both ranging and for guiding themselves, in addition to visual systems, which are the role of auxiliary arrays is really very important. And I have something to say there that I think is making a big difference in geophysical imaging. So the key fact in the key, let's say, theoretical fact in imaging with cross correlations is that we can actually recover information about travel times from noisy signals. We record what appears to be noise, we form cross correlations of noisy signals, and in there is real information. In principle, the Green's function of the underlying wave equation, if it's a simple situation like that, or in general something else like travel times. And that's the principle. That is the principal theoretical insight that we have. That goes back about 10 years, this realization, maybe a little bit more, 10, 12 years. But once you understand the mathematics and the physics of the problem, then you realize that this understanding was there a lot earlier. It just it wasn't part of the culture of imaging. There are certain mathematical tools, relatively simple in the beginning, like the stationary phase method, that allow us to interpret the universality of the behavior of cross correlations when in different situations. For example, the directivity, the energy that is coming to us, to the array, has directivity, and that allows us to deal with it. The stationary phase method does. And then the virtual source imaging that I've already mentioned is how to use auxiliary arrays to deal with very strongly scattering media in between, and how to remove the effects or to minimize the effects of medium inhomogeneities using auxiliary arrays. I have one more general set of comments that I want to make. We need enough ambient noise in order for the cross-correlation method to work. That's one fact. And of course, here I say it in a slightly more mathematical way, singular support of the time domain Green's function, which means getting the travel times out. Now here, in point 2 and point 3, these are the two different but very important applications of correlation-based imaging. When we know, as in geophysics, we know the locations of the sensors, the seismograms are located in certain places that we know in advance. We put them there. Then we can use correlation-based imaging to estimate tomographically the speed of propagation of the waves, whatever they are, whatever kind of waves they are, we can estimate their speed of propagation. So that is what I'm going to discuss here. And this was the breakthrough research that was done in the US and in France around 2005, and I will show that in the next slide. There is another application which is very interesting, and that is the one where we do not know where the sensors are located. We do not know where the sensors are. The sensors are out there with unknown locations. But we know where what the speed of propagation is. In the electromagnetic case, it would be the speed of light. In that case, we can use cross correlations to find the location of the sensors. So in other words, we have a method, a technique for creating a self-awareness of a sensor network which is more or less opportunistically or randomly dispersed in an environment. This is important in communications and in other areas. I have worked on that, but I'm not going to talk about it today. I just want to point out that the correlation-based method can be used there. And then the fourth method is the one that has potentially the most dramatic applications, and that is that cross correlations are not among noisy signals are not made at any one time. They can be made over a long period of time and sense changes in the travel time. So we can sense changes from what we estimate for the travel times to be today, a month from now, a year from now, and by comparing the changes, we can make some inferences, and I will come back to that. That's very important. For example, I will give you one dramatic application here that is in the process of becoming reality, and that is as a possible prediction of earthquakes or volcanic eruptions. So here's I will spend a little bit of time to explain to you what this is from the work that was done in 2005 with the Southern California seismic network. And the figures that you see here come from a review paper that was published in Leading Edge, which is the main journal of the Society of Exploration Geophysics, the community of scientists that do seismic imaging for hydrocarbon exploration. And so you can recognize this is Southern California. This is Los Angeles is here. This is the Nevada border, and this is a network of about 150 seismic stations. They're of the order of 10 kilometers apart, the seismic stations. What we do is we record the signals here at any one of the stations. We continuously record the signals. There are no earthquakes. This is in a quiet period. Of course, there's always small earthquakes, but we're not thinking of that. We're thinking of a quiet period, let's say. We record them here. They are recorded over a month. The signals, and then we form the empirical cross-correlation of the two signals. Let me show you what the empirical cross-correlation looks like. Here it is. Here you record the signal as a function of time at one seismic station, at one seismograph, and you record it at another. You shift the signal at the second one by a lag time tau, some shift in time. You multiply the two signals together, and you form the time average over some period of time, capital T. This is the empirical cross-correlation of the two signals. That's all that I'm going to be dealing with. Everything that I will be doing is just this, repeatedly calculated over different seismic stations for different periods of time, capital T, and for different lags. Okay? So now let's see what this looks like. When you calculate overall pairs of seismic stations here, you calculate this cross correlation and you plot the peak. You plot this cross correlation, forget about the peak, you plot the cross correlation as a function of the lag time, and you plot them arranged in the distance apart. These are the stations that are a distance in range. I think this is in meters here. No, this is in kilometers. So that's 50 kilometers, 100 kilometers, 150 kilometers, 200, 400, 500. This is in kilometers. And you can see that they more or less line up. The peaks, it's not quite a... First of all, there are many peaks. At any given distance, the cross correlation has many peaks. But there seems to be a straight line that can be fit through the data here. This straight line is a slope. That means it has the dimensions of, the slope has the dimensions of speed. So there is a characteristic speed. So the energy is propagating through here, through this ambient, through this medium, the Southern California surface. And the question is, what is this energy that's propagating and what is its speed? Now, if we take, there's a standard technique called travel time tomography. If we estimate, you will see another more detailed cartoon of this. If for any pair of stations here, we estimate, we extract the peak of the cross correlation. Where is the cross correlation having its peak? We extract this travel time, and therefore, for every pair of stations here, we have a travel time. We know where they are located. We know their distance. We know their location. And we have a travel time, so we have an estimate of a speed locally here, another estimate of the speed here, another estimate of a speed there. And from these estimates of speeds, from pairs of stations, we can consistently estimate an underlying speed, a map of speeds that looks like this. This is done tomographically in a consistent way, matching the data to some continuously varying speed. And you can see that the speed is, it turns out it's more accurate than similar maps that can be constructed using real earthquakes. No, remember that this is information, this is noise information. This is the kind of information that is thrown away, that the seismologists up until now, up until 5, 10 years ago, were not interested at all in this information. Now this information is providing velocity maps, surface wave velocity maps, that are more accurate, or at least as accurate as what we had before. For example, here in the Los Angeles basin, which is more or less a sedimentary basin, the speed of propagation is low, is of the order of 1.5 kilometers per second. This is the San Andreas fault here, and in areas in the desert, in the Nevada desert, which is compacted rock, you have fast speeds of propagation, and so on. This is an area that is interesting here. This is the area of South Los Angeles, Long Beach. It's very sedimentary. That's where the oil reserves are. The oil deposits are underground here. So let's look at the similar picture in Europe. This is from a paper in 2008, Geophysical Prospecting, from a group of very distinguished, it's a mixture of people here. The senior author is Campillo, who is a geophysicist in France, in Grenoble. And there's a mathematician here, Colin de Verdière, who does micro-local analysis. So it's a kind of an interesting, just to give you a few idea, an idea who they are. Weaver and Roux are specialists on ultrasound imaging. It's very interdisciplinary. They are not geophysicists at all. Mazarin is a geophysicist, is a former student of Campillo, and these other guys are geophysicists. So it's a very interesting study where the diamonds are the seismic stations of the Alpine network in Europe. And well, there are some seismic stations in Spain and so on. And from these stations, you can tomographically estimate the surface wave speed in Europe, and you can see that in the sedimentary valley of the Po River Valley north of Italy, the speed of propagation is very low, is quite low down here. In the Rhine River Valley, it's also very, very low. And then elsewhere, it's quite high because it's compacted rock. So out of what seemed to be useless information, the noise in the seismographs, we are able to extract information. Now, you probably have a lot of questions to ask. Let me just anticipate what your questions might be. So you should be thinking, so this is what all I did is I computed this. I collected data routinely. The difficult, just to point out, the non-trivial part is this, that the thing that held up doing this experiment or this calculation for a long time is the signal processing. Namely, how do you take this data over, let's say, over a month-long data, how do you calculate this empirical cross-correlation in an intelligent way so that, for example, you threshold out pure noise that doesn't contribute to the peak that you want to observe. You're not interested in this object except for the time at which it has a peak, and you want to identify this peak as accurately as you can. So that's what, it's the signal processing that goes understanding your data set and creating a decomposition of the signal and then stacking it over different segments, this empirical cross-correlation to get it as with the best signal-to-noise ratio that you can. So here are the questions that you should be asking, and for which the answers may not be obvious at first sight. First of all, what is generating the wave energy recorded in the noise signals? So what is it? There's a demon underground in the earth that is generating energy. What is generating the energy, the wave energy? Where is this energy coming from? And what is its structure? If there's energy, there are signals, they have a frequency content and so on. Well, it turns out the energy is from the breaking of the waves at the ocean. So the energy is from the breaking of the waves. There's no other serious energy to compete with that. So there's the energy is generated all along the coast here from the breaking of waves. And similarly in Europe, it is generated on the west coast of France for the breaking of the waves here, or from breaking of the waves here. And the energy is, and well, of course in England too here. And then the energy propagates from west to east like that. Has been converted to elastic waves, to the surface-guided elastic waves, and it's propagating. That's a very complex process. Surface-guided waves are waves in an elastic medium that propagate along the surface of the elastic body that we're considering, and they damp in the direction away from the surface. Those are surface-guided waves. But one of the phenomena that is particularly interesting here to show the complexity of what's going on is that we observe that the wave energy that's propagating, we observe from the data that the wave energy that's propagating indicates that the waves are dispersive, that the waves depend on the frequency range. If you use the frequency range of where the breaking of the waves is most active, in other words, you look at seismograms and you look at them, you filter them in the frequency range of 0.5 hertz to 2 hertz. That's the range of the microseismic activity. Then you find that the speed of propagation corresponds to surface-guided waves, which it's very difficult to say how they are generated because we don't really know what the underground is. So we know that these are the observation is that it's consistent with surface wave. It's consistent with the hypothesis that we are observing surface waves, but we have no model for tells us what kind of surface waves they are. We don't really know this, and if you look more carefully at the data, you will find that in other frequency ranges there are other waves that are propagating, also surface-guided waves. And occasionally you can even see body waves, P and S, compressional and shear waves. So that the information in the cross correlations is very, very rich. And we're just extracting what the signal-to-noise ratio allows us to extract. And we have, and everything is completely model-free up to now. I don't really know. I know that something is propagating with a speed, but I don't really know where the sources are. Really, I have no idea, or how they're being scattered and they produce what I see. And here I have a window in a very particular range. I'm talking about a regime of a few hundred kilometers. It's a regional scale, Southern California. Let's say 200 or 300 kilometers by 200 or 300 kilometers. I could consider something that's on a much smaller scale. I'll show you data for that, on a field level scale. Or I could consider something on the continental scale. Let's say everything that goes on the western part of the United States or of continental Europe. This is more continental, for example, here. The alpine data here is continental really in size, whereas the one that I showed you in Southern California was much more regional. So this is what we have, and the first thing that I want to explain, I want to show in a couple of slides, 2 or 3 slides, how it is that cross correlations are associated with travel times. With a very simple wave equation model, with the wave equation is a simple mathematical model, not at all at the level of complexity of what this data is, but it's simple enough to indicate that cross correlations are related to Green's functions. So let me explain that. First, here's a cartoon, which I think maybe I should have shown it a little earlier. So this is an idealized situation. And this is with very simple numerical simulations. I put the round circles here, the empty circles here, are sources of noise. So noise is being generated, noise in time, signals noise in time. These are point sources that emit spherical waves, which with a time variation that looks like noise, white noise, let's say. And then the signals are statistically independent for different spatial locations. And I add all these signals, I superpose them, and I observe them at location x1 and at location x2, and here's what I see. This is the signal, a piece of the signal recorded at x2, a piece of the signal at x1, a piece of the signal recorded at x2, and now I form the cross correlation between x1 and x2, and all of a sudden I see from simple numerical simulations that a peak forms here. There are 3 parameters that should be observed here, and the 3 parameters are, first of all, the time, the center time here that tells you that the peak has occurred at a particular time, and this time is the travel time between x1 and x2. That's the interpretation, the travel time between here and there. We haven't done the theory yet to explain that in a simple wave equation model. The second parameter that you should observe is the width of this blip here, the width of this, which controls the resolution with which I can estimate the travel times. If this travel time here, this looks like it happens at center 200, and this is of the order of maybe 50 units of time, 50 seconds, let's say. Then the resolution that I have is of the order of 200 plus or minus, let's say 25 seconds, something like that. This is what really controls my resolution. The third parameter is the height of this peak relative to the background level of noise, the peak to side lobe ratio, which is the signal to noise ratio. If this is low, I don't have a good way of estimating where the peak occurs. Those are the 3 parameters, and I have to fight to keep this. What controls the width of this? What controls it is beyond my control. What controls it is the decoherence time, is how close to white noise is the signal that is generated by the waves, for example, in the Southern California data. And so this I have no control over. This depends on the microseismic mechanism that generates the noise. And it's usually, it depends on the frequency band, it depends on the bandwidth of the noise. The bigger the bandwidth of the noise, so for example here, it was between 0.5 hertz and 2 hertz. That's the bandwidth. If I had taken a larger bandwidth, then I would have, this would be narrower. The problem is that when I take a larger bandwidth, then I lose control. Then I start to include other types of waves that are not the waves that I want to image or whose travel time I want to estimate. So I cannot arbitrarily increase the bandwidth of the signal that I'm considering. So I have to consider that. You will see in a few minutes what happens when I consider higher frequency, an analysis where I use a spectrum above 2 hertz. So that's the situation. Now, here's the mathematical model. I have a few slides that are more mathematical. Here's the wave equation. It's a very simple deterministic wave equation with a speed of propagation that is, let's say, known at first. Of course, in the end, that's what we have to estimate, the speed. And then the source of noise is the right-hand side of the equation, and we assume that this is a random function. It's a linear wave equation with a deterministic, with a random right-hand side. It's a very simple stochastic problem. This is a random function that has mean 0, statistical mean 0, and it has a theoretical covariance that is a function that indicates that these noise sources are uncorrelated for different locations in space, delta function in y1 and y2. The function theta here indicates the support. In other words, where theta is 0, there are no sources of noise, but where theta has support, is not 0, let's say is 1, there are noise sources. And this is the time correlation function of the waves, and here's where this parameter epsilon that measures the bandwidth of the noise relative to the bandwidth of the noise. So the epsilon is a ratio of travel times, the reciprocal of the bandwidth of the noise, which is a time scale, the decoherence time of the noise, as compared to the typical travel time between sensors. And we want that to be small. We want the travel time to be long compared to the reciprocal of the bandwidth of the noise. Otherwise, we cannot get a good estimate of the travel time. And so we introduced that explicitly as a parameter, a small parameter, epsilon. It's not so small. In the Southern California experiment, it's of the order of maybe 0.2, 0.25, 0.1, something like that. It's not extremely small. And in many situations, it could be even larger. It could be as much as 1/4. So nevertheless, the theory is, the theoretical part is based on an asymptotic theory when the epsilon is small. So this is the form of the noise, and now we can solve the wave equation using the Green's function, which is, we write a solution as a superposition of the noise sources multiplied by the Green's function. The Green's function is a deterministic solution. It's a deterministic function. It's a solution of the wave equation with the delta function, space-time delta function on the right-hand side. Causal Green's function is 0 for negative times. And in a homogeneous medium, we have an explicit expression for this. We put this in here. We then take this, we put it into the, this U, we put it into the cross-correlation expression, this one. And then for T large, when T is large, we can replace the time average by a statistical average because it's normal that there's enough decorrelation in time from this parameter epsilon that I showed you. So it's a very good approximation to replace the time average by statistical average. And then we get the expression that I showed here. So here I actually show the explicit expression that we get. This is the relationship between correlation functions and Green's functions. So here I specialize to a calculation that I can do explicitly. The previous calculation I could not do explicitly because I had the variable speed of propagation. And I don't have this Green's function. I don't have it explicitly. But when the c is a constant, I have the Green's function explicitly. It's down here. It's a delta function. The Green's function in a homogeneous medium is just a delta function that's propagating, that it peaks, the delta function that has a peak when the time, the running time, is equal to the travel time between x1 and x2. The travel time is simply the distance divided by the speed. The distance between the 2 points divided by the speed, that's the travel time. And so this travel time is an object that is characteristic of the spatial location of the sensors. The speed here is known. The background speed is c0. And this Green's function peaks when t equals its travel time. It has a sharp peak. And of course, there's a spatial dispersion effect because we're in 3 dimensions. The intensity of the Green's function diminishes as you increase x1. The distance between x1 and x2 increases. So here I specialize to a homogeneous medium, and I specialize to noise sources that are everywhere. Theta is 1. The support of the noise sources is everywhere. But since the support is everywhere, there's energy coming from infinity, and then I would have a problem with the wave equation with an infinite source of energy. So I introduce a dissipating mechanism in order to have a nice finite energy solution. And so there is an absorption time, T sub A, which is introduced here. And this equation now can be solved explicitly. Here's the Green's function. You can solve it explicitly. You can calculate these averages. It's an elementary calculation. And we find that the rate of change with respect, by the way, this C super 1 is a theoretical correlation function. It doesn't depend on capital T anymore. It's a theoretical correlation function. And the super 1 it's okay. You can ignore the super 1. It's because there's a possibility to calculate higher order moments too, like 4th order correlations, which I'm not going to show. So this is the rate of change with respect to the lag time of the correlation function is equal to the difference between Green's function, the 2 Green's functions, these are of course these Green's functions here, convoluted with the cross-correlation function. F super epsilon is the cross-correlation function of the noise sources, the time cross-correlation function of the noise sources. And there's a dissipation factor up front here. If the epsilon is very, very small, then the power spectral density of the power spectral function, the power correlation function, the power spectral density is very flat, or the correlation time is very small for the noise sources, then we get this, you can replace the f by delta function, and you can see that the rate of change of the empirically calculated cross-correlation function is approximately in the sense of epsilon being small. The symmetrized Green's function is the Green's function at lag tau minus the Green's function at minus tau multiplied by this decay factor. And that's the theoretical explanation of how correlation functions and Green's functions are related. This is the canonical calculation that explains this relationship. It's a very simple relationship in this simple model, but of course, in the real, when I'm dealing with real data, the situation is much more complex because I'm talking about elastic waves, surface waves. I don't even know what waves I'm talking about. I have no idea what Green's function I'm dealing with, but nevertheless, there's a characteristic time, some travel time, which means that there's wave energy that's propagating. And so this wave energy is propagating with a speed, and it's that speed that I'm estimating without really knowing what the waves are. So I'm making an inference about speed without a model. This is a new way of thinking that's dramatically different in geophysics from what we have been doing in the past. So here, so I have a slide to make that point a little bit more emphatic. What do we want from the models, and what do we expect what can we expect from the data? So now I want to really confront you with the idea of what what can models do for us and what do we expect from the data? So from the models, one of the things that is very important from the models is that, first of all, in this calculation, I assume that the sources are everywhere. I gave you a very idealized computation. I said that the noise sources are everywhere, absolutely everywhere. This calculation relied on this. It was a very simple explicit calculation at the level of an exercise in a wave propagation class. But in reality, if I go back to the Southern California experiment, all the sources are along the coast here. There's a very definite location of where the sources are. They are noisy, all right. They are not coherent because the waves are breaking and they are not systematically breaking at any one place here. They're breaking in location. They're breaking, you know, the breaking of the waves here and the breaking of the waves nearby is at more or less independent events if you're not very close. And then the breaking over time is also is noisy, looks like noise. So this is okay, but what about the fact that there are no noise sources anywhere else? What about that? Well, can be dealt with. So how does the directivity of the wave energy affect cross-correlation calculations? That's how, in relatively simple models, we can deal with it with a stationary phase method. We can set up a much more complicated mathematical framework, and in this framework, we can show that the directivity of the wave is not so important. I have a schematic later on. I think in my next, I will explain how this goes in a minute. From the models, how do we interpret the dispersiveness of the waves? The data tells us whatever waves are propagating underneath there, they are dispersive. So we're not dealing with body waves. We're not dealing with simple surface waves. We know that the original calculation of Rayleigh for a homogeneous half-space elastic medium, there the waves are not dispersive. The classic Rayleigh waves are not dispersive. But in a curved Earth or in an Earth model where the speed of propagation is slightly variable, increases slowly with depth, then the surface waves are dispersive. The surface of the Earth acts as a waveguide. The waveguide was first discovered around 1910, 1915 or so. It's a very important discovery in modern geophysics that the near surface of the Earth acts as a waveguide. So, for example, energy that comes from earthquakes, from elsewhere, eventually a lot of the energy gets into the waveguide and propagates over long distances along the surface waveguide. So all these are extremely complex phenomena and require some kind of a model for what does the surface of the Earth look like as an elastic medium. None of this is really necessary for what we might want to do, and I will explain the applications. If I start thinking in terms of models, I will go crazy with the complexity of what's going on. And so I put this in this context. Do we really want to fit surface wave models to the data? This is the traditional point of view of geophysics. When we didn't have a lot of data, and we made measurements, I can point to you, for example, the dramatic increase in research in this area, fitting surface wave models to data, came in the late 1960s. Up until that time, the models for the Earth and propagation of elastic waves in the Earth was a very limited subject. It was restricted to travel times. People would analyze in great detail earthquakes and arrival times from earthquakes. When did the pressure wave arrive? When did the shear wave arrive? A little bit later. When did the surface waves arrive? And there would be experts who would look at a seismogram, and let's say they look at a seismogram and they would very quickly tell you that this comes from South America. Let's say you had a seismograph in Europe, and you could, by looking at it, identify arrivals and the types of waves that were arriving. Then in the 1960s, shortly after the Nuclear Test Ban Treaty was signed in 1964, and atmospheric nuclear tests were prohibited around the world, then at the time the Soviet Union and the United States, the nuclear superpowers, and China started doing underground seismic tests. So in order to verify that there was compliance with the test, the geophysics community was asked to estimate the strength of the sources. That, for example, the United States in Nevada or the Soviet Union, wherever it was in Kazakhstan, they were doing the tests, they were not exceeding, they were not exploding devices that were exceeding a certain level. So then all the seismologists of the time, where there was an array in Norway, there was an array in Colorado, they were collecting data and they were trying to figure out, they knew where the sources of the energy were, but they wanted to estimate the strength of the sources. So it turns out that most of the success of this by the late 80s, early 90s, when the Soviet Union fell at the time, in the United States, there was a very accurate determination of source location. It had nothing to do with estimating models. There was absolutely no differential equations, elastic waves, none of this. It was just a very simple formula that an empirical Norwegian geophysicist came up with that focused on the energy of a surface wave that was measured by the array. It was a very accurate estimator of, it was a precursor of the kind of work that is being done now, where the geophysicists are massively abandoning model fitting. So from the data, can we identify other interesting travel times and peaks of the cross correlations? There are plenty of peaks in the cross correlation. There is not just a single peak in the cross correlation. You look at the cross correlation, it's full of interesting peaks. What are they telling us? If we can identify them with enough signal-to-noise ratio. That's a very interesting problem. It's all the rage right now. There's all the geophysicists everywhere, every single graduate student in geophysics at Stanford is looking for peaks in cross-correlations of data. And I'm sure that's happening elsewhere too. What about absorption and multiple scattering? Then people say, well, it's not just peaks in the cross-correlation. There's also damping factors that are important here. Wave energy doesn't propagate undiminished. It turns out that the damping factors are not important on regional scales, but they are important on continental scales. And damping factors are not only from absorption, from natural absorption, from conversion to heat of wave energy, but they're also associated with multiple scattering, conversion into incoherent wave energy. And so there's a lot to be learned about the ambient medium from estimating the decay of wave energy. On a continental scale, this has been done, can be done, and has been done, and it's largely without using heavily complex models. Now let me explain how stationary phase shows you what happens with when there is directivity of the sources. So remember that the sources in the Southern California experiment were on one side, on the coast. Well, here I put them all on the left side, and now here are two stations, two seismic stations. I measure the noise here. It turns out stationary phase tells you that if you take the straight line, let's say, if in the homogeneous background, if you take a straight line between the two receivers here, the two seismograms, and you extend it, if that extended line cuts into the region of noise sources, in other words, cuts into the coast, then you will get a peak in the cross correlation. Otherwise, you will not. In other words, there really will be some energy that's coming from the left towards the right. It crosses the x1 first, then it crosses the x2. And the signal that is recorded at x1 is what it is. The signal that is recorded at x2 remembers, is encoded in the signal at x2, that the signal first passed through x1. So the lag, the fact that the x2, the energy first went through x1 and then through x2, is recorded in the signals itself, and the cross correlation brings it out. Here, you do not get a peak. You get a very weak peak because there is no serious amount of energy that's going in the direction from x1 to x2. And here, this is not so important because it's the reciprocity if I interchange the role of x1 and x2. So here's how, for example, here's a numerical experiment which shows that when the two receivers are lined up like this, then the energy is clearly going through x1 and then going through x2. So there's really only one peak. It's not symmetric, as if you had the sources everywhere. The cross-correlation function has only a peak at positive lag time. Here, when you invert the situation, you put the sources on the other side and you cross-correlate x1 and x2 in this order, then you get the peak on the other side. And then if you have them if you have the sources parallel like this, then the energy arrives at x1 and x2 almost at the same time. There's no energy going up and down, and you get very weak peaks here. This is not a good configuration for determining travel times. You don't get a good signal-to-noise ratio here. So these kind of configurations of seismographs should be avoided. So I'll go back for a minute to this picture here. Seismic stations that are more or less, the line between them is parallel to the coast are useless. They are not very good. So they should be thrown out, because if you try to include them, it will only add noise, and it will make this image that you have here, this image of the underground velocity, more noisy than it has to be. Those are intelligent signal processing decisions. In practice, these are very important decisions, and they have to be done very carefully. That's where the game is being played by the practitioners. Okay, now let me show you the Long Beach data. This is now on a field. This is new research that I got from Biondo Biondi, is the director of the Stanford Exploration Project. It's a long-standing research project in seismic imaging, started about 40 years ago. And Biondo has many students, one of which is this guy Chang, who I took this stuff from a report, a preliminary report of the thesis he's writing. He gave it to me, so I'm citing it very carefully because it's very interesting work, and I don't want not to get his credit for him. So here's Los Angeles here, and this is Long Beach, South Los Angeles, and there's an old oil field there. There are about this is an area of about 8 by 4 kilometers. 8 by 4 kilometers, and the array has many sensors. On the average, about 100 meters spacing. It should be here. This is 100-meter spacing. And notice that there's the Highway 405, a very busy highway in Southern California, that passes right through this field. And of course, when you drive through it, you will see oil wells on either side of this. Now, you record, so there are recorded over many days noise signals in these stations, and you form cross correlations. And the question is, what information do you get out of this? So imagine there are thousands of signals recorded here. There are thousands of pairs of cross correlations, of cross correlations for pairs of seismic stations that you can form. What information can you extract from this? Well, first of all, we already know that we expect that most of the energy will come from the breaking of the waves on the coast here, okay, or even up here. But there's also other sources of energy. This is, of course, a much smaller area. The distance between the seismic stations is only about 100 meters. So here's a very interesting, let me spend a minute to explain to you what we are looking at. This is a different way of plotting cross correlations. So what do we do? So we take a distinguished point right around the middle here. Take a point in here in the middle of this array, and now calculate cross correlations between some distinguished point here, some seismic station here, and all with this as a center, one calculate cross correlations with all the others, axially with all the other stations around it. Calculate cross correlations relative to a center, to a point, to what's called a virtual source. Here's what you see. This one is plotted. So the color is, this is a plot of the cross correlation function as a function of the distances of, this is, the source is somewhere here in the middle. This is the cross correlation as a function of distance away, just like you see it here. This is the array. And the color indicates the peak of the cross correlation at a lag time of -5 seconds here and +5 seconds there. And you can see there's a very clear directivity. You get, at -5 seconds, you get the peaks over here. You don't get, that's where you get the cross correlations. You don't get cross correlations on the other side. At +5, you get the cross correlations over here. So what is the, and this is of course with the signals that have been filtered to be in a frequency range of 0.5 to 2 hertz. The speed turns out to be 250 meters per second. It's very low speed. That corresponds to definitely to a Rayleigh wave, to a surface-guided wave. And there's an anisotropy. This tells us that the source of noise is anisotropic. That's clearly coming from the coast because it shows this directivity, the effect of directivity. Now, if I go to higher frequencies, which is, I did not have the possibility to do it in the other data, in the Southern California data, this is it for the frequency range of 2 to 4 hertz. Then the speed of propagation turns out to be about 500 meters per second, and it turns out to be more isotropic here. It looks like a genuine point source that is propagating energy out, a virtual source, isotropic. What's generating this energy? Well, it turns out it's the trucks that are driving up and down 405. So this is energy that's being generated by the motion of by human-generated motion, by traffic on the highway. So the highway is acting as a source of energy with which you can image in a different way. And of course, it's different at night than it is during the day. This is for different lag times here. Now, you might say, that is fine. Now, what are you going to do with this? Why is this interesting? I've done this calculation. You've seen that I can create virtual sources. Are there any interesting applications of this? Why is every geophysicist up and down, certainly in the United States and in Europe, where the centers of geophysics are, mostly in France, why is everybody so excited about this? What's the reason? Why have they dropped everything else? Literally, they have dropped everything else they were doing, whatever it was. They have dropped it and they're doing this. Why? One application is a very practical one for the oil industry. And that is that if this was an active field, then this is characteristic of the underground. Remember that we are observing energy propagating, wave energy propagating. If the underground, the immediate, the subsurface structure is changing as it would be changing if I were extracting oil from underground, it would compact the underground area, this picture would change. So a time-lapsed version of this, if I calculate this figure now, and I calculate it a month later, and I observed very accurately, it turns out, small changes in these travel times, that's what this is telling me, small changes in the travel times. Then I know, for example, if the travel times have increased, what does that indicate? It means that the speed, if the travel time has increased, the speed has decreased, so that void has been created underground. If the travel times have decreased, that means the speed has increased and compaction has occurred. So I have very cheaply a way to know what is going on underground with time-lapsed versions of this. That's one application. Possibly a very important one, not the only application. There's another application that's equally important and possibly even more important, and that is that, by the way, what I just told you, this time-lapsed detection of changes in the underground structure of, let's say, of this oil field, which this array monitors, let's say, is model-free. I did not tell you what was underneath there. I do not know what is underneath there. All I know is that whatever it is, it has changed very accurately. And I know in which direction it has changed. Now, here's another application that is extremely interesting and has been used especially in the LA area, and that is that, you say, wait a minute, here I have a virtual source. I have a source that says that I imagine this is as if I have put a source of energy right here in the middle, and then I watch how elastic waves are propagating in a certain frequency, with a certain frequency content, in a region whose underground structure is completely unknown to me. So, for example, if I have a building sitting right here, the distance between these things, this blip, this red blip, this stations is about 100 meters. If I had a building there, I could use this passive information to find out how a possible earthquake would have interacted with this building, and what the response of the building could have been to an earthquake in a very realistic setting without me knowing anything about the underground. Because I don't have to know it. All I have to know is what the virtual source looks like. These waves know what the underground is. I do not know. And I can use them to find how these waves are going to interact with the building that I placed there. That's being done, and some very interesting things have been done with buildings at Caltech, for example. The library building at Caltech, sensors were put in it, seismic stations, and the cross correlations were obtained. And for example, one of the things that came up was that the effective speed of propagation up and down in this building is of the order of 300 meters per second. So in other words, the library at Caltech behaves like a dispersive medium with a typical speed of propagation in this range, actually in the range of 0.5 to 2 hertz, has an effective speed. And not only that, but you can actually study the response, the response of the building to virtual sources that can be placed wherever you want. You can place a virtual source near the San Andreas Fault and simulate very accurately from data what the response of the building would be to a real earthquake. So the potential applications are dramatic. The only thing that is holding back this application is the expense of planting seismic stations, because you need a lot of seismic stations in order to have data with enough resolution to make good predictions about how the buildings will respond. But the cost of a seismic station like this, a few years ago, was of the order of $5,000 to $10,000. It's going down all the time. So I can imagine that in the next, very soon, you will be able to deploy on a large scale seismic stations that are less than $1,000. And what's a few $1,000s to get accurate data compared to the kind of destruction that you can have from a real earthquake that brings down buildings? So now let me finish. I have maybe another few minutes, 2 or 3 minutes, to explain the last application. This is the application that is mathematically. You could have also asked another question. Is this interesting mathematically? That's for the mathematicians among you. And the answer is, of course, it's mathematically interesting. All these things are, when you start asking, of course, you need models. You have to put models. You have to ask, for example, are they inhomogeneous? How important are the inhomogeneities on the medium? I put a title for my talk, Imaging in Complex Media. Well, where's the complex medium? What I've really focused attention on is to point out to you that I didn't really have to know anything about the medium to extract this information. Now, I want to focus on the role of the medium and ask the following question. This is a cartoon now, not real data anymore. This is a typical situation that I encounter with marine data. So I have I have here on the surface a source receiver setup where the sources are on the surface, let's say with a marine survey of data where I have a ship going over, let's say, 10 kilometer by 10 kilometer wide area on the surface, and there's an air gun that periodically releases energy, a spherical wave energy, with a frequency content of about let's say between 5 and 50 hertz in that range, and it's going down underground. It's going down maybe of the order of 5 to 6 to 7 kilometers underground. It strikes, of course, the surface of the bottom of the water, and then there are multiple reflections up and down. Some of the energy goes in, and then you want to image some area down a few kilometers. That would be the area with some anomaly like a salt dome that traps hydrocarbons. So this is, I want to image a reflector deep inside the medium from the surface, but the problem is that the medium is not homogeneous in between. It's a highly inhomogeneous medium. The surface of the Earth is a very complex medium. Is a medium with fluctuations of the order of 15% in the speed of propagation. It is a very complex elastic medium. And a typical shear wave speed is of the order of 3 kilometers per second. It increases slightly with depth, but the medium is highly uncompacted. The fluctuations have been estimated from well-logged data to have a correlation length of the order of 3 meters in the surface of the Earth. Is an extremely complex medium. So when we try to image through it, it's a miracle that we can get good images. Well, somebody had an idea, and I will tell you who, it wasn't me, that maybe it's a good idea to put another array somewhere. The most obvious place to put a second, an auxiliary array, is at the bottom of the sea. So you have the surface with this moving towed array that is taking measurements all the time, or for a long time. And then you have at the bottom a second array, which is displayed here. For example, this has been done at the Gulf of Mexico. A very expensive array was laid down at the bottom of the Gulf. Or if there are holes from previous explorations, this doesn't have to be horizontal, this array, the secondary array. If you had a previous exploration and there was a hole several kilometers down, you can put passive sensors down there. This is passive. So you have then in this situation a source of energy at the top, is releasing energy, and then you record secondary signals here passively at xq and at xq prime. The signals will look very noisy because the energy is going through this very complex medium. Now, the question is, can we do something that will take out the effect of this random medium? And here's how you do that. Turns out you can do it. Let me skip this. The two geophysicists that did this were Bakulin and Calvert in 2006. And that's a very interesting paper. It's difficult to read because it wasn't explained clearly, but since then, several other people, including ourselves, realized what's going on. I won't explain the details. I don't want to explain the details of what's going on here. Let me skip this slide and point out what the imaging functional is. This is probably to many of you is not a known thing. So, how do you image? If I had the surface array, if I only had the traditional array, this is the traditional surface marine survey array. The source is here, the receiver is here, and this is a very large, many sources, many receivers are moving around. Then I can form an image. The classic way to form an image is using this function. This is called the migration functional. So this is 95% or 98% of all imaging out there, seismic and otherwise, radar, is done with a formula like that. You take the data on the surface. This is what you have as a function of the source location. and the receiver location, you record the data as a function of time. This is the echoes that come back to the surface and are recorded as a function of time. Now you take this time variable here and you replace it by a travel time. Namely, the travel time from the source to a fictitious point where you want to image, y super s, s for search. Okay, this point ys is roaming through the region that you want to image. You want to find out where the image might be. So you take the travel time from the source to this search point, plus the travel time from the search point to the receiver. This is the travel time down to here, the travel time up. And you sum this expression over all sources and over all receivers, you form this image. And when this function has a peak, that indicates that there's a reflector down there. That's classical imaging. That's the thing that will fail because of the inhomogeneous medium. Unless you have an extremely large array and you do some interesting processing, this is traditional seismic imaging. And of course, if the depth is not very large, it will be okay. I can talk about this for a while, but let me move on to show you what you can do much better. How do you use the auxiliary array? When you use the auxiliary array, you take only the data on the auxiliary array at 2 points, xq and xq prime, for a surface source at xs. So you form the cross correlation. You form the cross correlation of the data at xq and xq prime. This is, you take the data at time t, the data at time t plus tau. You sum empirically, you form the average over a time window, capital T. You sum over all sources, and you call this the empirical cross correlation over all the surface sources between xq and xq prime for a lag time tau. And now, instead of using the surface data, you use this C sub t, this correlation matrix. You use it in exactly the same formula, the migration formula that I had before. You use it exactly the same way, and you form this image. And this behaves in a spectacularly transparent way. This is a result of a calculation with Chrysula Tsonga, with whom a lot of this work has been done. And so here's the numerical simulation. This is a simulation with realistic numbers from the geophysical context. I won't go into the details. I'm running out of time. I won't talk about the details of the numbers here. But this is the surface array here. This is where this object is. This is the secondary, the auxiliary passive array down here. This is the very complex simulated random medium. And here's the image in the traditional way. You don't see, this is a little window. I plot this function I in the vicinity about the 20 by 20 wavelength window around here. The wavelength is about 100 meters. So you see nothing. But when you do the cross correlations and form the image with the cross correlations, you pick the scatter perfectly, as if there is no random medium, as if it's a homogeneous medium. This is almost like a miracle. And so, understandably, this has revolutionized seismic exploration. It's an unbelievably, there's so much going on in this field. It's just unbelievable what's going on. I don't want to explain in detail. By the way, this is correlation-based imaging, all right, because you saw how I use correlations. But the reason that this works, that it takes out the effect of the random medium, is a very subtle reason that, just tell you some of the physics. Here, it appears that by the time the signals arrive at the secondary array, they appear, see, when you have a source at the surface, it generates a wave. The wave goes through the medium, it generates partial waves from the multiple scattering that all arrive at different times over here and they generate what looks like noise. And then it looks, oh, this random medium is acting like a randomizer of the source, a randomizer of a coherent source of energy at the top, this air gun. By the time it comes to the secondary array, it appears like noise. And then you cross-correlate noise, oh, it's like before. It isn't. There's a subtle difference here because the previous one, the main thing that it was calculating was the peak in the cross-correlation. The peak in the cross-correlation was the travel time between sensors. But the travel time between sensors is not an interesting quantity here. I want the travel time between the sensors and this scatterer. I want this travel time. This is the one that's going to give me an image. And the question is, this peak, the peak in the correlation function corresponding to a lag that is equal to the travel time between some element here and this reflector, is a very small peak, it would seem. But it turns out it's not a small peak. It's really a very large peak. The dominant peak, which would have been the peak between two stations here, is actually a very small one. And that's because you can reinterpret the cross correlations of the waves here, of the signals here, in terms of a time reversal, a process by which the random medium above is essentially neutralized. And that's why you end up with a very, very clean image here. So there's a very interesting, mathematically interesting, complex process that explains why this works. People understand it, I think. We wrote, Jocelyn Garnier and I wrote a paper on this. The time reversal work goes back to work that with Chrysula Tsonga we did about 10 years ago to explain why this object behaves very well when you have the configuration that I showed you. And then we did also the theory for this effect, for this the interpretation of the virtual source imaging. I just wanted, I'm going to go to my last slide, my concluding remarks. And I will say that cross correlations is really interesting. Is a new way to deal with seismic data, extract information from noise for what used to be considered wasted information. It was data that was never used. It was just collecting there. Nobody was interested in the noise, the quiet in between earthquakes. And now, all of a sudden, this information is absolutely all important. The role of passive auxiliary arrays all of a sudden is becoming important. The anomaly here is that there is, to this day, 7 years after the Bakulin and Calvert paper, and many years after other papers have been written in this area also, we don't have a single set of real data from auxiliary arrays in order to see this. The companies that have the data, the oil companies that have the data, are keeping their data, and that's a sure sign that they are getting good results. Because if they were getting bad results, the data would be all over the place for everybody to see. So they're guarding their data, and the clear signal is that the data is really giving you good information. And of course, the theory, we have done the theory, and we see that the theory is dramatically shows that the data should be very good with a wide range of parameters and configurations. So we have excellent theoretical reasons to do it. One of the things that we want to do with this is we want to apply the same method with radar, with satellite, to use these passive arrays to image satellites up in the sky, taking out the atmospheric effects with sources of radar sources on the ground. That's an interesting application. We don't know that it's going to work because the parameters are so different. We cannot do simulations. It's a very difficult problem, and we need some good physical understanding or some guesses to see why it works. I want to finish with one more slide, which is another one of these dramatic effects. I told you that there's a possibility of predicting earthquakes with this. Campillo in Grenoble did a very thorough study. I will explain this in a second. Did a very thorough study, a historical study of earthquakes in the last 20, 30 years. Took all the data that he could. He studied cross-correlation effects, and he found that, roughly speaking, a posteriori, by tracking travel times from noise data of earthquakes along, let's say, the San Andreas Fault in Japan, and other places where earthquakes have occurred, you cannot really predict earthquakes, at least not with the data we have now, not unless we deploy more seismic stations. And for example, the earthquake that occurred in 1977 to the east of Beijing in China was completely unpredictable by these methods, according to Campillo. But certain other earthquakes were perfectly predictable. Now it turns out, with modern instrumentation, they were able to predict the eruption of an earthquake in Réunion, in an island in southeast Africa. It's an island out here in the Indian Ocean. There is a very active volcano, and they deployed seismic stations around here. This is the volcanic area here in the island. This is a larger, this is about a 10 kilometer, it's more like 50 kilometers by 50 kilometers. And so here is a window in which you see the deployed seismic stations. And they kept recording signals constantly, forming cross correlations, and then doing time-lapsed evaluation of travel times. And they observed about a week before the eruption of the earthquake that the travel times were being altered. The travel times that were being estimated were shortening, which means that there was a compaction of the underground, there was the rising of the magma. And they were able to predict a week before the eruption that the eruption was about to come. And this was a dramatic event. This was about a year ago that they made this prediction. And I think this is a dramatic development that with good instrumentation, we may have as much as days lead time for the onset of an earthquake in the near future. I'll stop here. Thank you. Yeah.
So the fact that you can use white noise for uncorrelation, spectroscopy kind of things, to study materials, I guess is well known for thermal noise in Brownian motion, surface waves, and capillary waves, and all this. That's been used for many years now. So why is it that it's only coming now for geophysics? Is there any specific reason?
For capillary waves, I wasn't aware that it has been used, correlation-based methods have been used for...
That's how you detect it. I mean,
I wasn't aware of this.
With light scattering, for example, and we use correlation functions to measure velocities of waves and things like that. And they
Yeah.
are thermally excited, they are KT excited. So in a way,
Light scattering is, you shine light, right? It's...
that does not produce the waves, it just reflects them.
Yeah. I don't know what to tell you. I can tell you that in the ultrasound, this is the last 5-10 years. It has been used. Another application that is very recent is in the ultrasound situation is where you embed ultrasonic sensors in aircraft structures, and then the vibrations in the aircraft structure are constantly being move around the plane structure, the wings, the fuselage, and you're recording constantly the noise passively, and then you form cross correlations, and from the changes in the estimated travel times between from the cross correlations, you can detect alterations in the structure, like cracks in the medium. That's a relatively recent technology. They're talking about doing the same thing with the human body, where you can embed ultrasonic sensors in the human body and detect, let's say, I don't know, maybe changes in structural elements in the human body, perhaps the formation of tumors. To be honest with you, I don't know these medical applications, but that's the extent of my understanding of this. And the radar applications are also emerging with radar in the synthetic aperture radar in the 10 gigahertz regime, the possibility of using passive sources for taking out atmospheric effects, as I mentioned in the last example. Now, why the molecular thing that I cannot answer that. Yes?
You mentioned that the actual source of noise in the southern Heraklion basin, it's basically energy flow
It's energy flow that comes from the breaking of the waves, yes.
So that basically means that the detectors that we have are sufficiently sensitive. Because, I mean, I was confused in the presentation that you made because, you know, typically in astrophysics, when we talk about noise, it's sort of like completely uncorrelated noise that you cannot make any predictions. Here, the way I interpret it is as if you have some sort of like random signal that comes from various directions, and you decipher that using cross-correlation techniques. How does the energy flow that you have from waves? Can you for example, see seasonal variation?
Oh, yes.
And how does that compare with the energy that you would have from heavy traxes passing next to your detector? Right?
Well, let me answer that last thing first. The difference between the energy that's generated by traffic that is going through this field here. This is Highway 405 that's going through the middle here in the field. The difference between the energy that's breaking coming from the coast and that one is in the frequency range. In other words, when you look at the frequency range of 2 to 5 hertz, 0.5 to 2 hertz, which is the frequency range that is normally associated with the breaking of waves, the microseismic activity generated by the breaking of waves, then you see this kind of virtual source formation, which is consistent with the directionality of the waves coming, let's say, from the coast moving inwards. That's what you would expect the source to be. That's the cross correlations would be one-sided. As I mentioned, when the waves are going from right to left, the sources are directed. And then when you go into the frequency range of 2 to 4 hertz, much higher frequency, then you see a kind of you lose this directivity. You see a more isotropic virtual source, and the interpretation is that that's because you're on either side of 405 here, and so the trucks are generating noise that is more or less isotropic relative to where the point source, the virtual source, is located. I think that's a very clear interpretation of separation between the different sources of noise. Now, what was the first part of the question?
Whether you detect seasonal variation.
Oh, yes. You very much detect seasonal variations. Not only you can detect seasonal variations, you can detect hurricanes. If the waves that are breaking let's say there is a hurricane in Hawaii or in the Pacific somewhere, and there are a lot of waves that are hitting the coast, you can immediately see that from these cross correlations. You can, Campillo, I think it was about a few years back, they detected a very large activity. The noise activity was all of a sudden very high, and they were able to there is a very easy way to detect from where the noise was coming, the directivity of the source of the noise. And they found that it was coming from the southeast. And it turns out at that time there was a typhoon in Southeast Asia, and from noise cross correlations they detected it in the Alps. So this was very accurate, very sensitive. There are many other things that you can do with this. This is incredibly sensitive to small changes. That's why the possibility of detecting small changes in the structure in the vicinity of faults is so important, because for detecting the onset of some kind of emotion, because there is small scale changes in as the slip is about to occur in a fault, and the speed of propagation changes microscopically, and you can detect it with these things. The question is, in what frequency range should you look? There's some interesting geophysics going on. What kind of sensors should you deploy? Where should you deploy them? What frequency range you should look at? What kind of cross correlations you should construct that are going to have the signal-to-noise ratio strong enough to be a good, a sensitive detector of the onset of an earthquake? These are non-trivial questions, highly non-trivial questions. Yes?
Could you elaborate more on this satellite problem you mentioned?
The satellite problem is this. There are of the order, at any given time, there are of the order of about 20,000 man-made objects that are flying around the Earth, at about between 200 or 300 and 700 or 800 kilometers elevation. And they are being tracked for decades now with arrays on the ground, with low frequency, relatively low frequency arrays on the ground, with microwaves in the range of below, I would say, below 200 megahertz, something like that. They stay below the region where microwaves are being absorbed by the ionosphere. So there is very good tracking. Now the question is, these objects are relatively small. Some of the satellites are of the order of meters big. They're not very big. And then you want to image them, not only to detect them, that there's something there that is going at very fast from one end of the horizon to the other, but you would like to also image it. How many hands it has, what does it look like? Now you can image it optically, but optical imaging is very sensitive. You can only do it during the day. When the object is flying at night, you cannot see it. You have to deploy the cameras in a certain way to be able to see it, and so on and so forth. So the question is, can you image high-flying, 500-kilometer flying satellites passively with radar? And so that's a challenge, because you have to take out the atmospheric effects. You have a limited time. You have a limited time to observe the object because it's moving very fast. And there are several trade-offs here. It's a very complicated problem. We don't know if it's going to work. And it's very hard to do numerical simulations because you're trying to take out atmospheric effects where the wavelength for the radar would be of the order of 3 centimeters, and you have to go maybe 10, 15 kilometers through a turbulent atmosphere with a 3 centimeter wavelength. You go, the tropopause is about 15 kilometers. You have to go about 15 kilometers to see a quiet atmosphere. And you have to take the atmospheric effects out. And the atmospheric effects are not static in time. So it's not clear that it can be done. I think it can be done, but it remains to be seen. Yes? Yes.
What did you do?
This was, it's just, basically, we recorded. It's a crazy situation. So this is the traditional array. You have, let's say, it's a cartoon. You have the source here, the receivers there. You measure data. And then you want to image some reflector down deep here. This is the traditional data. And the imaging function, this is the migration formula, is this function. You record the data coming from source at xs, receiver at xr, as a function of time. This is the time variable here. You replace the time variable by the travel time to a fictitious point located at y super s for search, where you would expect a reflector to be. And then you form this image over some window where the object might be. And where there is a peak, then the real reflector is, a peak to this function. That's the imaging function. That's a very well-studied functional. I have studied it. Many others have studied it. This is the Kirchhoff migration functional. This is not time reversal. This is a functional that the theory for this started being used about 40 years ago. I would say mostly in geophysics. The theory was developed in the 1980s by people like Norman Blystein and certain other people at the University of Colorado and elsewhere in Greg Bailkin, who was at Courant Institute a little before, Bob Burridge. So these are the people who developed the early theory for this functional, that this functional is really a truly imaging functional. And with Chrysoula and Liliana Boccia and I, we studied this functional in inhomogeneous media and in random media, and we showed that it can fail. So our theory was that this functional doesn't work in complex media, and we tried to find how to improve it. And so one of the things that we realized recently, of course, there are many other things, I'm skipping a lot of details of what happened in between, but then we said is, go back, and now, suppose you have a secondary array, and now you record signals here. Forget about the data on the surface. Record only on the secondary array, which is passive, and form cross correlations. Form cross correlations like that, and sum over all sources. Only at the bottom, xq and xq prime, only at the bottom. And now use the exact same functional as if this was the primary data. And you sum over q and q prime. It's a passive array. You use this functional. And like magic, this thing doesn't care that you have gone through a random medium, through an inhomogeneous medium. It's just amazing. I mean, it turns out many years of theoretical research in random media where it's as if they were just waiting for this application to be used. And it perfectly shows, the theory shows why the effect of the medium is essentially removed completely. That was in this paper that I showed right here, that paper. No, this paper here. So, do you want me to say a little bit more physically why this works? Or what would you like? Because this is something that is amazing in a way. It's a miracle. And we don't have real data. The people with the real data, Bakulin and Calvert, who were, Calvert was a senior researcher at Shell when they worked in that problem. He left, I don't know where he's now. Bakulin is now at Saudi Aramco. Calvert, I think he passed away. But when they did this work, they were at Shell. And this paper I was the referee of that paper because it appeared in a volume where I have a paper also. And I was furious about that paper. I couldn't understand what they were doing. I was too quick to reject it. But the idea was there, and I only realized later that I had a good idea. One of the reasons why I didn't like the paper is because they use synthetic data. It's okay for me, for an academic, to use numerical data. But when a guy from Shell does numerical simulations, it's just absurd. They should be using real data. They were not using real data, so they were not convincing to me, and the paper was written in a very bad way, conceptually speaking. But they had the idea, and when we finally tried it with synthetic data, we generated very carefully. It worked extremely well, and we understood why it worked. And this is because, now I will explain the physics. The physics is like this. It's really an issue of reciprocity. So what it says is, if you have a source here, and the waves goes through this very complex medium, and you record the signal here and the signal there, and you form the cross correlation. This is exactly the same thing as having a source here, a receiver there, and then recording here the signal that goes all the way up to the top is recorded at this array. It is time reversed, conjugated, and sent back in. So this is a time reversal process. This expression here, you look at it, you can reinterpret it in an entirely different way. You can reinterpret it as if one of the xq's was a source, the other xq was a receiver, and the xss was a time reversal mirror at the top. It's an identical interpretation. If you were doing this experiment, you would be writing down the same expression. And so this problem becomes a problem in time reversal. In other words, a problem that was studied by the French in 20 years ago with ultrasound and ultrasound only. And it was never done in a geophysical context. So what are the effects there? The effects are that when you do time reversal in a random medium, in other words, you start from here, you have a source here, you send the wave through this medium, you record it at this array, you time reverse it and you send it back in. Then the physical phenomenon is that you're running the wave equation backwards. So the wave equation doesn't care that it's going through a random medium. It's going to go and focus back to its source if you run it backwards. If you watch in the movies, sometimes in CNN, they show how a tennis player, they play tennis, and you're not quite sure, is it running forward in time or is it running backwards in time? During a long sequence of volleys, during the serve time, you know that's the beginning of the thing. But when they are volleying, if they play that movie backwards, you cannot tell. It looks just like it's going forward. Well, it's because of the reciprocity of the wave equation. When you run the wave equation backwards, it looks just the same. It's another wave equation. So the wave equation, when you take the waves from here, you run it through some very complex medium, you record it here, you time reverse it, you run it back through the medium, you time reverse the wave equation, it's going to go back to the source that generated it. It doesn't care what the medium was. So therefore, when you cross-correlate a signal between here and here, it's as if you're looking at the time reverse field in the vicinity of the source. And since the wave that is being time reversed is going to go down and focus at its source, in the immediate neighborhood, when you try to measure it, it will be essentially null, because it wants to go to where it was generated. So you will get almost, at the secondary array, no peaks anywhere else but in the vicinity of the source that generates in the vicinity of XQ. And therefore, if there is another peak that is coming from the reflector below, you will see it loud and clear, because the other peaks have been eliminated by the time reversal. And that's the reason why you get this. Because you have eliminated all the other peaks, and the cross-correlation has a pristine, a very clean peak, right at the travel time where this reflector is. And this is an unbelievable physical phenomenon. I don't know if the people in molecular business, they have thought of it. They haven't thought of this good. Finally, something they haven't thought of.
Actually,
yes?
Since the early 80s, it was known that fusing electrons have a very clear signature of time reversal paths. It's called this sort of weak disorder and weak localization physics. So, to cut a long story short, you have an increased probability for the electrons to go back to the original
There you go.
where they started.
Yeah. Well,
This has to do with
but the question is, can you measure it?
equivalent.
Yeah. Man, you can imagine that this is so, but can you measure it?
Sorry.
You can imagine it can be measured.
Yes, first of all, it's calculated, and then it is easily measured microscopically.
Macroscopically.
Microscopically, just measure the conductivity of
Yeah. Ah, no, that's not good enough.
the piece of material.
No, that's not good enough. Because that's really the point here. Because these macroscopic measurements are incoherent, and they don't have the ability to image. They may be good for... I suspect that these macroscopic measurements are interesting for other things, and I can try some ideas on you, knowledgeable, but they are not good for imaging, because they're incoherent. You take out...
For this case, but this is what I mentioned, this is where I think the whole thing started from. Then they took this for classical waves, because there's an equivalence with electrons. I think this was done mostly in France.
Who did this?
Roger Menard, maybe this.
Ah, no. I know the work of Roger Menard, but I don't think it's this. By the way, Campillo and Menard are in the same university, and so they talk to each other all the time. So this is... no, I don't think so. But I think, however, what you mentioned about the bulk conductivity and how that is affected by this process. That's interesting. That is more related to this time lapse. That would be interesting to observe, for example, macroscopic changes, sensitive changes in the bulk conductivity. That could be a very interesting way to detect microscopic changes in the material, or small changes, for example, phase transition changes from bulk thermal measurements. That could be interesting, for example. Okay, thank you very much.